joints and fractures. And these fractures are what we're going to be focusing on in this talk.
All right, we'll try one.
Can you hear me now online? Better?
I can hear you on the phone. Let's use this.
Okay.
You just have to speak up a little bit more, probably.
Okay, I'll try to move this a little closer. Just let me know if it's hopefully people can hear me. Okay, that's okay if you missed that, because now we're gonna get into the real stuff. So getting into the background, so the basin. All right. Okay, so basin evolution. So the Paradox Basin. The Paradox Basin formed during Pennsylvanian Permian time as a flexural coralline basin on the southwestern flank of the Uncompahgre uplift. This was a basement chord uplift that was active during ancestral Rocky Mountain time, and that created a flexural load that created subsidence that allowed for a thick sequence of evaporates and shales to be deposited, and that is the Paradox Formation, those evaporates and shales. Shortly after the Paradox Formation was deposited, sediments began to be shed off the Uncompahgre uplift during Permian time, and that sediment loading initiated passive diapirism that created these elongate salt walls that formed parallel to the Uncompahgre front. And these salt walls are now exhumed to the surface, and so we can look at deformation at the surface right at that salt sediment contact. Since that time, there was some major modification to the basin during Laramide time, during late Cretaceous to early Eocene time. On the Colorado Plateau in general, there was a series of basement chord uplifts that formed. You can see them, a few of them here surrounding the basin. And that is kind of the characteristic of Laramide deformation, is basement chord uplifts. But in the basin itself, we see kind of a different style of deformation. We don't see these big basement chord uplifts projecting into the basin. What we see instead is a minor modification of the salt walls. And we'll talk a little bit more about that. Okay, so this is a cross section going through Salt Valley just to kind of show some of the geometries. So this is the salt wall of Salt Valley, the Uncompahgre uplift that created the accommodation space necessary for the basin. The one thing I wanted to point out is the Permian through Triassic, so the red and purple units here, have significant thickness variations along the flanks of the uplift. And that is because they were deposited during passive diapirism. So as these were being deposited, they were actively squishing the salt out like a tube of toothpaste. And that allowed for these mini basins to develop on both sides of the salt walls. So we can see that in the sedimentary record based on these kind of halokinetic sequences with significant thickness variations in and around the salt walls. By the time we get up to the Jurassic section, for the most part, we see them being deposited and pretty isopacously consistent across the top of the salt walls, suggesting that by kind of latest Triassic, early Jurassic time in the basin, most of the passive diapirism had shut off. These salt welds have formed where the salt was squeezed out to a zero thickness, closing off salt flow pathways. And so that basically locked the salt walls in place at that time and allowed for sediments to be deposited and just start burying the basin. But we still see in the Jurassic and Cretaceous sediments, we still see a 15 to 20 degree dip along the margins of the salt walls. And that's attributed to this Laramide rejuvenation of the salt walls, where you then kind of loaded what had northeast shortening, and that created, that allowed the salt to internally deform and amplify and folded the overlying sediment. So that folding that you see in the salt walls is attributed in the Jurassic and Cretaceous units is attributed to Laramide shortening. Okay, so these fractures that we're looking at in Northern Salt Valley, when did they form? So they're within the Jurassic Moab tongue member of the Entrada Formation. So they were deposited after the primary passive diacharism had kind of shut off for the most part throughout the basin. And the major players here are going to be the severe and Laramide deformation potentially that could have formed these, that could have created the stress field that formed these fracture systems. And if we look at, so this map here kind of shows more regionally the Western Cordillera. What this surface is it's the top of basement. So you can see the big Laramide basement chord uplifts. So the Paradox Basin is right here. This is the Monument uplift, the San Rafael swell, the Uncompahgre uplift, and you can see more significant Laramide basement chord relief in the Wyoming province to the north. The severe frontal thrust is shown in red, and it's not, we don't see a lot of severe thin-skinned related deformation further inboard, but this kind of Laramide deformation that surrounds the basin is thought to be the cause of that folding, and these fractures likely formed as secondary structures to that folding. So zooming in here on the Colorado Plateau, this is just a map that maps out the anticlines, synclines, and major monoclines and uplifts on the Colorado Plateau. And you'll just notice here in the Paradox Basin, which is in this kind of hashed pink area, that you don't see major monoclines cutting through like you see in the rest of the basin. And instead you kind of see these folds that parallel the salt, suggesting that the salt and the presence of the salt was playing a role in affecting how deformation was propagating in the basin. So this is just an example of what Laramide deformation looks like in other parts of the plateau. So this is what you typically think of. This is the Hunters Point monocline. So you see this kind of gently dipping back limb and steeply dipping front limb. And these are cored by basement involved uplifts. And they trend, this is the Comb Ridge monocline, they can trend for hundreds of kilometers. So we're seeing a significantly different style of deformation happening in the basin at this time. So this image here just kind of shows the patterns of folding that we see that are, so what this surface is it's the base of the Dakota sandstone datum. So because it's a Cretaceous unit, this unit was pretty much only deformed on the Colorado Plateau by Laramide. So the deformation patterns that we see kind of show what the Laramide did to that surface. It hasn't really been altered significantly since then, with the exception of the intrusive bodies. So you can see here that, again, you have these major Laramide uplifts that were happening in the basin. You just kind of have these little folds in the Cretaceous that are running parallel to the Uncompahgre front. And so this is zooming in on the Paradox Basin. It's just the same surface. And again, I'm just pointing out that instead of having these big basement chord uplifts, you get these more symmetrical folds that kind of orient themselves along the salt walls. Okay, so why is their deformation looking different in the Paradox Basin? And the idea is that salt is playing a major role. Because salt is so weak, it has really anomalous mechanical properties, a very low strength, a brittle ductile transition at 100 meters depth. And so we basically see salt deforming via ductile mechanisms under very low differential stress, and it can't sustain very much differential stress. It'll just start to internally deform. And so as you apply this regional tectonic stress, the salt is going to deform and soak up a lot of that stress. And so a lot of that stress is being accumulated in the internal salt deformation. Okay, so what we want to look at is, okay, so the salt is being internally deformed via active diacharism. What is going on in the rocks directly adjacent to that salt? How is the stress field being altered there? So in the Paradox Basin, we have a unique environment where we're able to look at the salt sediment interface at the surface because it has been exhumed. So we can look at these fracture patterns that formed during that late Cretaceous to Eocene shortening event and look at what the stress field looked like adjacent to the salt. Okay, so what is crustal stress and what we're looking at here? So we're looking at stresses in the Earth's crust that's driving deformation, and the orientation of those stresses can determine the style of faulting that we see. So both the orientation and the magnitude of stress determine how the rock's going to deform. So what we're doing is we're looking at evidence in the rocks themselves and trying to back out and interpret what the stress field looked like from that from those strain patterns. So here we are. This is the northern end of Salt Valley. This is the outcrop of the Jurassic Moab tongue sandstone. This is the unit that contains the fractures that we're interested in. The Valley City Fault, which cuts just up, runs semi-parallel to the outcrop. This is a late stage salt wall collapse fault. So it's basically a kind of a proxy for the salt sediment interface or the location of that. And this unit is dipping about 20 degrees off to the southwest. So what you can see here in the satellite imagery is a kind of pervasive large scale jointing. And this jointing formed during basin exhumation. What we're interested in are these smaller scale shear fractures. So shooting off behind Henry here is an example of what the joints look like in the field. They kind of erode out to these fissures, but they cross-cut a series of shear fractures that have slick insides, evidence for fluid flow, and this is what we're interested in looking at. So what can we tell from these conjugate shear fractures? So what we're looking at here is we're looking to look at the orientation of the shear fractures and relate that back to a stress state. So when you think about that in Mohr circle space, and if you haven't looked at Mohr circles in a while, what we're looking at here is trying to relate a stress environment to rock failure. And so a single circle on a Mohr diagram represents a stress state. When that stress state intersects a failure criteria, the rock will fail. And so what this diagram is demonstrating here is that under different differential stress states, critical differential stress states, you get different types of failure. So we're going to look at the patterns of failure that we see and try to relate that back to the stress environment that would have created those deformation features. Okay, so just a little bit of background on linear and nonlinear failure criteria. So in structural geology, most of us are taught primarily this linear failure criteria. And this linear failure criteria or Coulomb failure criteria, it allows you to kind of more simply relate the stress environment to when that rock is going to fail. So this is kind of the basis for the Andersonian idea that every time a rock fails, the failure plane is going to form at 30 degrees from sigma 1 because this angular relationship between the point of failure and the stress environment remains constant. But with a nonlinear failure criteria, you would expect that kind of to systematically change. And so this has been shown in experimental testing where we see kind of this, as you increase the confining pressure, you see an increase and a change in the failure angle. So as they increase their failure angle here, you see an increase in the failure angle with the magnitude of confining pressure. But this is something that hasn't really been shown in a natural environment, at least in any sort of systematic way. And it has significant implications for trying to relate failure angle to differential stress magnitudes. So if you look at the upper part of this diagram here shows the linear failure criteria for two different rock types versus the bottom half of the diagram shows a nonlinear failure criteria for the same rock types, and these are both experimentally constrained failure criteria. And the interpretive implications of using linear versus nonlinear, you can see that with different differential stress magnitudes for intact rock failure, for the linear failure criteria, you always get the exact same failure angle. But when you apply a nonlinear failure criteria, you see a systematically increasing failure angle with increasing differential stress. And that has to do with this nonlinear relationship between the point of failure and the differential stress magnitude. So looking at the trends that we observed in the strain pattern at this location, so we're going to kind of work our way down the outcrop, starting at the nose closest to the Valley City Fault or closest to the salt wall, and recognize the pattern as we get further away from that from that Valley City Fault. And each one of these distance bins is about 100 meters. Okay, so right up next to the Valley City Fault, we see conjugate shear fractures that have a highly acute dihedral angle of about 20 degrees. For kind of the Andersonian mechanics or with that linear model, we always expect the conjugate dihedral angle to be about 60 degrees. So that's highly acute. And it also has a normal orientation. So the acute bisector of the conjugates is the orientation of sigma 1, and sigma 2 tracks the intersection line, sigma 3 tracks the obtuse angle. So this allows us to see the stress regime we're in, which here it looks like we're in a normal stress regime with a highly acute dihedral angle. So we're going to keep an eye out as we move down the outcrop for changes in these two strain patterns. So a little bit further away, we're still in a normal stress regime where the acute bisector is vertical. But here we start to see the dihedral angle just slightly increase from 24 up to 31. And we'll step out a little bit further. Again, we see a slight increase in the conjugate dihedral angle, but we're still in a normal stress environment. And we'll move down a little more. Here, we're starting to see a little bit of a mixed and confusing signal. So you can kind of start to tease out a dihedral angle that's slightly larger. It's harder to really confidently say what type of stress environment we're in at this particular location. There's just a lot of scatter, but it looks like we're shifting away from that normal stress regime. And now as we move further down, it looks like we're solidly in a strike-slip stress environment. So the stress regime has changed. And our conjugate dihedral angle is still increasing. And as we continue to move down, we'll stay in the strike-slip. The conjugate dihedral angle is approaching more of an Andersonian type angle. And again, that trend just kind of continues. So as we move across the outcrop here, we see two main trends in the strain patterns. One being the trend in conjugate dihedral angle, which seems to be increasing as we get further from the Valley City Fault. And the second being the orientation of the conjugate intersection line, which represents the change in stress regime, where we see it kind of flip rather than a systematic change. It seems to flip around that kind of 200 to 300 meter distance from the salt wall. So here are those results plotted on cross plots. So each one of these points is one of those specific field locations that I showed you. These bend intervals are just every measurement I took within that distance interval from the Valley City Fault, which fall in pretty good agreement with each other. So we see a pretty linear relationship between the distance from that Valley City Fault and the conjugate dihedral angle. Whereas the plunge of the intersection line, when it's near zero, that would be a normal stress regime, and when it's vertical, it would be a strike-slip stress regime. That seems to be more of a flip at about 200 to 300 meters away from that Valley City Fault. So first we'll discuss the change in conjugate dihedral angle. So we want to think about whether or not this change in dihedral angle relates to a nonlinear failure criteria and potentially has implications for differential stress magnitude within that 400-meter distance from the salt itself. So here's the previous experimental work that has been done, again, just to show the relationship between failure angle and differential stress. And this is in a laboratory environment. So they were able to relate an increase in failure angle to an increase in differential stress. And you can see that failure angle increasing here with increasing differential stress or confining pressure. We see the same trend in our field results with distance from the Valley City Fault. We see that the failure angles are systematically increasing, which leads us to think that that this is related to an increase in differential stress as you move further from that salt sediment interface. So the idea being that the salt is internally deforming and there's a stress equilibrium across the salt sediment interface. And so as you approach that salt sediment interface, your differential stress magnitude is systematically decreasing because there should be a differential stress magnitude of 0 inside the salt itself. So we see a decrease in stress magnitudes approaching the salt, and that's shown, exhibited by the change in dihedral angle across the fault. So we wanted to try to relate the failure angles we were observing to an actual stress magnitude. So we did a bunch of geomechanical tests on the Moab tongue sandstone to try to define a nonlinear failure criteria for that rock unit. So we did Brazilian tests, uniaxial tests, and triaxial tests, and these were all done to define a failure criteria for the intact rock. And so the results from that show, a failure criteria, but the significant thing is the very low tensile strength of this rock unit. So initially, when we were seeing those highly acute conjugate shear fractures, we were thinking that that might have significant implications for fluid flow, suggesting that those fractures may have formed in a partially tensile environment, which would have had partial opening and partial shear components, which would have really allowed for fluids to flow a lot easier. In the field, we didn't see any direct evidence for hybrid failure or partial opening mode failure. And that may just be because the tensile strength of the Moab tongue is so low that even under low differential stress conditions, it's still failing in shear. But if you had a stronger rock type adjacent to salt that had a more significant tensile strength, you might expect to see enhanced fluid flow due to hybrid failure adjacent to the salt wall. Okay, so we're trying to use that nonlinear failure criteria we defined to relate the failure angle we observe to differential stress magnitudes. The problem with that is the failure criteria we defined was based on intact rock in a laboratory setting, so it's not taking into account fluid pressure, pre-existing weaknesses in the rock, so it doesn't really represent the strength of the rock mass, and that's what we're really trying to get at, is what's going on with the strength of the rock mass. And so engineers have developed and use something called the rock mass rating to try to scale the strength of their rock, the strength of intact rock to an actual rock mass. And they get at this rating by going out to the outcrop they're interested in. It might be a slope stability study or something, and they can measure and take these different direct measurements and come up with a rock mass rating. And typical rock mass rating values fall between 20 and 80. The point here is that there hasn't really been a way to accurately scale this strength in a natural geologic environment. But what we see is for intact rock, the differential stresses that we get at each one of these stations. So this is the failure angle that was calculated at each field location. And based on that nonlinear failure criteria for intact rock, these are the differential stress magnitudes that would have been required to create that failure angle. And for intact rock, it's, you're getting up to 600 megapascals of differential stress, which is really, really high. But once you start applying these rock mass scaling parameters that engineers typically use, even getting down to 50, you're getting below 100 megapascals. So although we're seeing this observation and this trend, we can say that it's likely due to a reduction in differential stress magnitude, but we can't say very much about that magnitude unless we develop a good way to determine the scaling parameter down to a rock mass. Okay, so this is the results plotted on the Moore diagram. So here you can just kind of see how we're doing this graphically, the idea being where this failure angle here is related to the failure angle we observe in the field. So that allows us to back calculate differential stress magnitudes in theory, but we really need to have a better rock mass scaling method to be able to say anything significant about the magnitudes themselves. All we can really say based on this is that we see the trend and it's likely related to differential stress magnitudes. We just don't know what those magnitudes actually look like. Okay, the second trend we observed is the change in stress regime. So you'll remember that up close to the salt, we were seeing normal fault stress regime. Further from the salt, we see a change to a strike slip stress regime. But remember, we were thinking these happened during shortening, northeast shortening. So how do we explain this change in stress regime as we get close to the salt? And is it even possible or likely that these formed during compression, during regional compression? Okay, so we wanted to get a more comprehensive coverage of the shear fracture orientations because we wanted to apply a modeling approach where we can, in the model, induce a far field Laramide stress state, allow the salt to deform, and see if we can recreate these stress regimes. So in order to benchmark that model approach, we wanted to get a more comprehensive coverage. So went out and flew a drone, and that gave us imagery with high enough resolution where we could remotely map in the point cloud these fracture patterns. This was better because in the field, like I said, these joints create massive fissures and it's really hard to get good coverage on the ground. So we were able to add more coverage. So in here in yellow are the field where I was out actually in the field measuring, and blue is the measurements we extracted from the point cloud. And these were binned into spatially binned, and then did a stress inversion for each bin based on the fracture data to pull out what the stress regime would have looked like. And based on that, this diagram here shows in blue a normal stress regime, in green a strike slip stress regime, and in yellow kind of a mixed result. So you can see that the trend holds up where, once we get to be about 300 or so meters from that fault, we see a change from normal to strike slip. Okay, and so we are looking to apply a elastic boundary element stress model where, again, we're applying that far field regional stress. So where sigma 1 is oriented northeast, and we allow the salt to deform and we see what the perturbed stress state is on an overlying observation surface. And so the steps that we need to do this is first the field-based analysis, which is done. And then we needed to build a 3D structural framework as model inputs, and then run the geomechanical model. So in order to build the 3D framework, built a section of cross sections, a series of cross sections across the region. So this area in the center of the cross section space is the deformed outcrop. So I constructed a series of cross sections. They're shown over there on the left that show the geometries at depth. And so zooming in on one of those here, and this unit here is the Moab tongue. So this is kind of the scale of that outcrop. And you can see that it's exposed right over in this location. it's exposed over this kind of underlying salt wall shoulder. So this salt wall shoulder is underlying our outcrop. Okay, but we needed to reconstruct these back to Laramide time because that's what we're trying to model here. So I just did reconstruction to get it back to what it would have looked like in late Cretaceous time. And again, this is our Moab tongue unit up there. And we did this for all of the cross sections, and that was in order to create this 3D model that was restored. And these 3D surfaces is what's needed as model inputs into the boundary element model. So that this here shows late Cretaceous, and then Eocene. This is the Laramide amplification where we see the salt wall contract and rise, and then that folds the overlying Moab tongue sandstone. So these are the surfaces that we're using. And then of course, this is after modern day dissolution and collapse. Those are those normal faults. Okay, so now we have the framework and we can use these as model inputs. Now, again, we want to look at the elastic response to a change in shape along the top of the salt. So what I did was I took the Cretaceous configuration and the Eocene configuration and subtracted the two, and then applied that vector difference to each point on the surface and so you're basically prescribing a specific motion everywhere along that surface, and you can view the elastic response to that stress change along the observation surface above. This is basically what's happening. These are the dislocation vectors in the model. So again, we're kind of laterally contracting and vertically rising the salt wall, and the Moab tongue sandstone is overlying that, and that's what we're observing the stress change due to this this movement. Okay, so what we can see here, this is after applying that change in the model and there's also a regional boundary condition that is representing that Laramide stress state. And so what we're looking at here are perturbed stress vectors. So sigma 1 is plotted. So you can see far away from the salt, it's representing that northeast orientation. And as you get over the salt wall, it moves to a vertical position, which would be that normal stress regime that we see over top of the salt wall. Okay. So kind of to conclude all of that, the first takeaway is that this is a really unique environment to observe nonlinear failure in a natural geologic environment. So among structural geologists that care about this sort of thing, it's been debated whether or not a nonlinear failure criteria is related to failure angles in a natural environment. And it's been really hard to show that just because it's hard to think of a geologic environment where you can see multiple differential stress magnitudes on an observable scale. And so this was a really unique environment where we see a rapid change in differential stress due to being adjacent to a salt wall under tectonic loading. And we're able to observe that systematic trend in failure angle that's associated with a differential stress environment. So that was the significance of recognizing that pattern and what that means. But more work needs to be done before we can actually relate it meaningfully to actual stress magnitudes. We can say that is what is, we can see that pattern, but we can't relate it to a stress magnitude without having a scaling parameter for the strength of the rock mass. And then getting into the state of stress around a salt body under tectonic loading. So the first thing is that reduction in differential stress. And so the idea here being, so again, at the bottom, we look at distance from the trace of the Valley City Fault, which runs parallel to the underlying salt wall, and the differential stress magnitude. These are calculated based on a random rock mass rating. So the magnitudes themselves don't really matter. It's more just like them relative to each other. And what we can see as we move away from the fault is a slight increase in differential stress and then a rapid change. And this is just based on the failure angles we observed. And our interpretation of that is that whenever we see that rapid change is when we cross over the salt shoulder. So we're getting further from the salt more rapidly at this point. So that's the first trend, and that's what we're relating it to. The second trend is the change in stress regime. So again, what I'm showing here on this first slide is the regional stress environment, where we're in a contractional stress environment. Recent and older work has shown we're likely in a three-dimensional stress state during to explain the regional Laramide deformation patterns that we see, where sigma 2 is slightly larger in magnitude than sigma 3. And we would expect to see contractional reverse faulting forming in this far field stress environment. When we get closer to the salt wall, what we see is sigma 1, far field sigma 1 being reduced, but it still remains locally sigma 1. Far field sigma 2 is also reduced, but it's reduced a little bit less in magnitude than sigma 1, because really what the salt is responding to that far field sigma 1 most. But it's reduced enough to locally change from sigma 2 to sigma 3. And this new stress environment, and sigma 2, which is just burial or loading, it remains the same. Or sorry, sigma 3. Sigma 3 remains the same, but it changes to sigma 2. And so what this does, this change in stress magnitudes, it flips the stress regime from that far field shortening to locally to strike slip. And then when we go even further and closer to the salt, we see that again that far field sigma 1 is reduced the most, and it's reduced so much here to be locally sigma 2. And then far field sigma 2 is reduced, but reduced a little bit less than far field sigma 1. And it's reduced locally to sigma 3. And far field sigma 3, again, is burial and it stays the same, but it's locally now sigma 1. And so that is how you get this normal extensional stress environment above the salt wall, is our interpretation of what's going on with the change in stress regime. So the takeaway here is that near salt, you see kind of weird strain and stress environments. Even in a shortening environment, you might expect to see normal or strike slip faults near salt. And it might be explained by by the deformation that's happening internally in that salt that's kind of changing the local stress state. And finally, this elastic modeling approach. This has typically been done mostly for looking at stress perturbations adjacent to faults. And because salt has such a high strain and it deforms plastically, you can't really use this elastic modeling to model salt deformation itself. But our application to it here, where we're looking at stress perturbations in the rock mass adjacent to salt, it seems to be producing the same patterns we're seeing. So it seems to match our observations in the field. So this might be a numerically simpler and computationally less heavy approach to looking at perturbations due to salt deformation in model space. Okay, so that's all I had. I'd like to thank my collaborators at Arizona. George and Amanda have been amazing, as well as Dave Farrell at the Southwest Research Institute. He's helped a lot with the nonlinear failure stuff. And Seth Busetti at Aramco, he has provided the proprietary modeling code that was manipulated and used in this study. And John Kemeny, who's also at Arizona, he's a geological engineer and had helped with the deformation experiments. The tech research group at Arizona, I was when I was working in the basin, part of kind of a larger group that was focused on paleo fluid flow evolution in the basin. So I was really lucky to learn a lot from people with different backgrounds and different areas of expertise in kind of an integrative way. Some various funding that I received, And these are the two papers that one out, one in prep, that are focused on the work that was presented here today. So happy to take any questions.